Okay, let me show you the contents of this video which I'm going to cover. First, I will introduce the topic. I will tell about the LTI systems. Then I will talk about the various time domain and frequency domain analysis of LTI systems. Then we will see how we can create the MATLAB graphical user interface to implement the LTI system analyzer using the MATLAB application guide. And then I will explain the MATLAB code of callback functions of various GUI components. And then we will do the program simulation to see the various outputs. So let me start, but before going ahead, I recommend you to watch following these two videos. Although these two videos are not directly related with the LTI systems, but for more exposure to the GUI development, you can refer these two videos. The first one is about the device control using the DTMF signals and the MATLAB app designer. So here I have used the MATLAB app designer to create the graphical user interface. This video is available on the link which is given in the description. The second video is about the producing colors with the RGB LEDs using Arduino and MATLAB. Here I have also created one graphical user interface with help of the MATLAB guide. So the link is also given in the description and you can also click the video card above. So now let me start the topic. So the LTI systems, of course, are the linear time invariant systems. These are the systems which follow the linearity and the time invariance. So let's see what are the linear systems. The linear systems are those which follow the homogeneity and the superposition principles. So let's see what is homogeneity. Consider the LTI system shown below. So here you have the LTI system which has the input xt and the corresponding output yt. So for this system, if let's say input is xt, then corresponding output is yt, and if input is multiplied by some factor a, then output is also multiplied by the same factor a. So for the input a xt, the output is ayt. So then the system is said to follow the homogeneity. Now let's see what is the superposition. For input x1, the system gives the output y1, and for input x2, the system gives output y2. If I sum these two inputs and give this to the system, let's say x1 plus x2, then corresponding output of the system is y1 plus y2. If it happens, then the system is said to follow the superposition or additivity. Both homogeneity and the superposition can be combined together like this. So for let's say input x1 output is y1, for x2 output is y2. Then if input is ax1 plus bx2, then linear system will produce the output ay1t plus by2t. So here you can see that multiplying with a and b, we are having the homogeneity, and by adding the two signals, we are getting the additivity or superposition. So now let's see what is the time invariance. So if the input xt produces the output yt, then if input is delayed by some time, let's say capital T, then output is also delayed by the same time. So that is true for the time advance also, t plus t, that will produce the y t plus t. Okay, so it says that the system properties do not change with the time. So the system which follow both linearity and the time invariance, they are known as the LTI systems. So the LTI systems actually can be characterized entirely by a single function that is known as the impulse response, and it is represented by the ht for the continuous time systems and by hn for discrete time systems. So here you can consider both the systems. So this is your continuous time systems which has the input xt and corresponding output yt, and it has the impulse response ht. You can consider this discrete time system having the discrete input xn and the corresponding output yn, and your impulse response is hn. So here continuous signal means your signal is like this, and corresponding output is also same analog, and in case of discrete you have the input which is discrete in nature. Okay, so for any input xt or xn, the output can simply be obtained by the convolution of both input and the impulse response like this. So that you can see in this equation. So for continuous time system, the output yt is obtained by the convolution of input and the impulse response st, and same is for discrete time system. Now we can represent these two equations in the frequency domain also. So if you take the Laplace transform of the equation 1 and the Z transform of equation 2, the same two equations can be represented by equation 3 and 4 in the frequency domain. So this is the equation 1. By taking Laplace transform, your convolution becomes multiplication. Similarly, your convolution becomes multiplication here in Z transform also. So this is how your complicated convolution becomes actually the easy multiplication in the frequency domain. So from equation 3, okay, we can find the ratio of xs and ys. So hs equal to ys upon xs, that is the Laplace transform of output to the Laplace transform of input. If you consider all initial conditions to be the 0, then this hs is called the transfer function of the LTI system. And of course, the inverse of this transfer function is called the impulse response of LTI system. It is a very important function that characterize or describes the whole system. Similarly, we can write the equation for discrete time system also. So hz equal to yz upon xz. So analysis of LTI system is actually the easy, and transfer function plays very important role in it. So the roots of the numerator, okay, they are called the zeros, and the roots of the denominator are called the poles of the system. And as you are aware that these poles and zeros are very useful in analyzing the system stability and the time response behavior of the LTI systems. So the transfer function is utilized to analyze the time domain behavior and the frequency domain behavior of any LTI system. Okay, now let's have a look on various analysis types for LTI systems. So here I will just consider some basic analysis for these systems. So if you consider the time domain analysis, we have these few important and basic analysis. The one is the time response analysis, where you consider the output of the systems for various inputs. For example, if you give the impulse, then what output is obtained from the system. So that is known as the impulse response. Similarly, for step input, we get the step response, and for ramp input, we get the ramp response. And for error analysis, we concentrate on the steady state error of the system, and generally we talk about the various coefficients. They are known as the error coefficients, such as static and dynamic error coefficients. And the one important is the stability analysis. So for that, we concentrate on the root locus method and the Routh-Hurwitz criterion. And similarly, in the frequency domain, we have the following important analysis. So first one is the frequency response analysis, where we go for various plots such as Bode plot, polar plot, log magnitude versus phase plot. And with these plots, we can go for the stability analysis, where we find whether the system is stable or not, and what is the amount of the phase margin, gain margin, etc. The same plots help us to find the stability of the system along with the Nyquist. Okay, so Bode plot, polar, Nyquist, and the log magnitude versus phase plot, and which is also known as a Nichols plot, that is log magnitude phase plot. And then we have the various techniques of modifying the frequency response of the system. So for that, we have the various compensators such as lag compensators, lead, lag, lead compensators, where with the help of these compensators, you can actually modify the frequency response of any LTI system to get the desired output. So now let's see how we can create a MATLAB graphical user interface to implement these basic LTI system analysis. So here our objective is to develop a GUI in MATLAB that will include the following types of responses or analysis for any LTI system. So these total eight analyses we will try to cover. So let's see how this will be created in MATLAB. So this is the glimpse of the GUI which I have created in the MATLAB. So here you can see that these are the axes, okay, where all the plots will be shown, and here you can enter the numerator of your transfer function. Here you can enter the denominator of your transfer function, and when you press this button, the transfer function is displayed here. For example, you have this transfer function, let's say s plus 25 upon s square plus 5s plus 25. So this transfer function can be easily entered here. First we will enter the numerator. We will enter only the coefficient of the numerator. So here the coefficients of numerator are only 1 and 25. So we will simply enter 1 space 25, and for denominator we will also enter its coefficients, so 1, 5 and 25. So when we press this find TF, means transfer function, the same transfer function is displayed here, and from here we can select any plot type. So if I select impulse response and press this compute button, the impulse response will be plotted here, and if I choose root locus, your root locus plot will be displayed here. This you can see in this figure. So here I have entered this numerator 1 and 25, 1, 2, 25. Pressing this find button, find TF, this transfer function is displayed here. You can see s plus 25 upon s square plus 2s plus 25, and when I select this root locus radio button and pressing this compute button, your root locus is displayed here. Okay, so this is the GUI which we will implement in this video. And now let's see how we can create it. So this we will create using the MATLAB guide application. So that guide application can be opened by simply executing this GUIDE on the command prompt. So when you execute it, you will get this type of window in the MATLAB. So here in this left panel, various GUI components are given, such as this push button, radio button, text fields, these axes, button groups, text field, checkbox, etc. So you can just simply pick and drop in this window, and this window is resizable. So here you can see you can resize it depending on your requirement, and you can simply place these components here. Okay, so I will show you this in MATLAB, and this is how I actually I have placed all these components. So this axis I have placed by from this button. Okay, so from this button simply click it, press it and drag and drop here. Okay, and you can resize it also depending on your application or requirement. And this text is taken from this button txt, that is a static text, and this edit text field I have taken from this button. So here you can see that edit is also written, edit text field. The same is also taken from this button, edit text field. This is your push button, find TF, and that is taken from this button, and this is also a push button that is also taken from the same button. And this is actually the one button group. So the first button group is taken from this button. Okay, so this is the button group. So button group will create a space, it's a blank space. In that blank space you can insert the radio button. So this is the radio button. So you need here 8 radio buttons, so you can pick 8 radio buttons and place here one by one. And in the MATLAB I will show you that how you can change these names. Okay, by default they are radio button 1, radio button 2, like that, and you can change them very easily. And one important thing is from programming point of view, that is a tag name. Actually each GUI component, these are known as actually the GUI component. I mean this text or axis, the edit field, or radio buttons or these push buttons, all are known as the GUI components, and each GUI component actually has a tag name. So the tag name is important because of which you can write their corresponding callback function in the MATLAB program. So you should be very careful about it. So in my program, actually the tag name for this axis is axis 2. In your case it may be the axis 1 or something else, so just remember it. And for this edit field, my tag name is edit 1. Okay, edit 1. Although it is default, you can also change. And for this text field, I get the tag name edit 2. For this push button, I get the tag name push button 1, and for this it is the push button 2. And for this button group, you get the name UI button group 1, like that. Okay, and for each radio button, you will get the radio button 1, radio button 2, 3, 4, 5, 6, like that, their corresponding tags. So that these tags I will also show you in the MATLAB. So let me jump to the MATLAB and show you how you can create this GUI. So this is my MATLAB window. So you just have to type the GUID guide and press enter. So when you press enter, this dialog box will appear and it will ask to open your existing, or you can choose the create new GUI. So you just choose the new GUI and just press OK, and this window is created. Okay, so here you can see that this gray shade part, so this is the default size of your MATLAB GUI. So you can simply resize it to any size depending on your requirement. And now I will place my GUI component. So first I need the axis to have the plots of various analysis. So simply I will have this axis simply by picking and placing here and then resizing. And then I want to give the title to this GUI. So this TXT, that is a static text, simply drag and place here, and you can resize it. Okay, name change I will tell you later. And now I want the edit field for entering the numerator. You can resize it like this, and similarly for denominator you can resize this, or you can simply duplicate also to match the size actually. Otherwise for every GUI component you have to manually make them equal in size just for good looking. And a text field is also needed to display that transfer function. And then button group, one button is also, radio button is also there, which I have placed. So the radio button is also there. So this is push button. So this is one push button, and there was a second push button here for computation of the analysis. So these two push buttons, and then draw the button group. So this is the button group. Okay, just drag and drop here, and you can resize to your requirement. So this is the button group, and where you will place all the radio buttons. So you can choose the radio button, simply drag and drop. So the first radio button, and then second radio button, third radio button, like this. So you can place all the 8 radio buttons corresponding to 8 analysis, right? And now let me show you how you can change the names. So for example, that I will change the name of this static text. So simply double click it. So when you double click it, the property inspector is opened. So this is the property inspector. Okay, so in the property inspector you just locate the string. So string, you can see that static text is written here. So whatever is written is here, the same is displayed here. So you can give any name, let's say my my LTI analyzer. Okay, so you can see that it is changed, my LTI analyzer. You can change its size. For example, the font size is just 8. You can change this to, let's say, 12. So its size is changed, and you can also change its color. Okay, so right now it is black. You can have any color. For example, you can choose the red. Okay, so this becomes red, right? And similarly, you can change the name of these edit text. So just double click it, and here edit text is written, and you do not want to write anything here. So just simply remove it, edit text. So it will be a blank text field, so that you can enter your coefficients of numerator. And here what important I was talking about is the tag. So just see the tag is here, and tag is the edit one. Okay, so here you can see that tag is edit one, and by the same name the MATLAB will recognize this text field. So when MATLAB will write the program for this GUI, it will write the code for this text field by the name edit one. So that is important. So if you want to access or write the MATLAB code for this text field, edit text field, then you have to refer the callback function corresponding to this edit one. So you can change it, but let it remain as it is, but you have to remember that edit one belongs to which text field, right? Similarly, you can change the properties of this second text field. So simply remove this edit text string, and now you can see that the tag for this is edit2. Okay, so this will be known by the name edit2. Now push button, simply double click it and locate the string. This is the string, and here you can write find tf, what I have written in my demo GUI. So this is find tf. You can change its size, color also, and the font from here. And now see the tag. The tag is push button 1. Okay, so the MATLAB program will identify this button or GUI component by the push button 1. And similarly, this last button, push button, here I have written the compute. So I can change its string to the compute. So it is changed to compute, and now see the tag. Its tag is the push button 2. Okay, so just remember their tags. And similarly, now when you double click this radio button, you can also see their corresponding string. So here radio button is written, and you can change its name to, let's say, impulse response, like this. Okay, so this becomes impulse response. So similarly, you can change the name of all the 8 radio buttons, and now remember their corresponding tags also. So this is how you can create your MATLAB GUI using the guide. So now you can save it. Let's say save into current MATLAB directory or any other directory of your choice. So let me I save here, and this is saved. And once you save it, you will see that MATLAB has written the MATLAB code for it. So this is automatically generated. Okay, this is automatically generated. So now let me show you where are the corresponding callback functions. So let me locate it. The first few lines are common. They are written for every GUI. So just you locate your corresponding callbacks. I mean the edit one, that was the first edit field. So this is the edit one. Okay, so you can see the function edit one callback. So whatever code related to that text you want to write, you can write here. So you can write here, right? for that code. And don't write anything in the create function, okay, only in write the callback function. And similarly, this is the edit to callback function. So if you want to read whatever written or user writes in that edit area, to grab that you can write the corresponding MATLAB code here. And now push button 1 callback is here and push button 2 callback is here. Okay, now here you could see that callback for added 1, callback for added 2, callback for push button 1 and push button 2, but you are not able to see the callback for those radio buttons and radio button group. The MATLAB by default does not provide the callback, but you can create here. Just go back to this GUI layout and just right click on this button group. Okay, so when your mouse cursor becomes this flower, you just right click and go to the view callbacks, right? So you will see the these few options like create function, delete function, button down function, size change function, and see the last one, that is a selection change function. So you have to click the selection change function. So when you click it, and you can see that MATLAB has written the corresponding callback. So this is the callback, which is the UI button group selection change function. So for those selection, you will write the corresponding MATLAB code here. Okay, so in the next slides, I will tell you what are the codes which you have to insert in these callbacks. So now if you run this program, it will create the GUI. Okay, it will create the GUI, what I have just created. But when you enter something, nothing will happen because I have not given any callback. So if you click this button, nothing will happen, okay, because I have not written any callback code in this program. So just remain this program open, and now you have to write the corresponding codes for each callbacks. So let me show you the codes for these callbacks. So this is the callback for the edit 1. Okay, so this is your edit 1 where you will enter your numerator. So this is what the MATLAB has written automatically, and after that you have to insert these 3 lines only. So num equal to text scan get h object string. Okay, so here whatever is written, like let's say 125, these 2 numbers are written in form of the string, and I am reading these string in form of the numbers using the text scan function. So these number 1 and 25 will go into this variable num, but that will create a cell array. So that cell array is converted into the matrix simple array, normal array with help of the cell to mat. So that will go into the variable num. But since I have to use this numerator across the callbacks, okay, so I have to create a handle. If you simply write num equal to, then this will be the local. So because it has to be used among the various callbacks, so it should be available to other callbacks functions, I mean across the callbacks. So you have to create the handles.num and then just update the object and handles. Okay, so only these 3 lines you have to insert for this edit 1 callback. Now come to the edit 2 callback. Similarly, you have to insert these 3 lines. These lines are automatically written by the MATLAB. So whenever user will enter the numerator coefficients, so these numbers will enter in these denominator variable den, and now I am making it handles.dn so that it can be used across the callbacks, and then updating the handles. And now let's see the push button 1. So in this push button, when you press this button, find TF, your transfer function is displayed. So when you enter the all numerator and denominator and pressing this button, this transfer function is displayed like this, s square plus 2s plus 25. But where this has to be displayed? This has to be displayed in the text, static text. So let me go back to the static text, this was the area which was the static text area where this transfer function will be displayed. So whatever you compute, this has to be a reference to this text area. So you should find the tag name of it. So the tag name of this is text1. So this area has the name tag name text1. So once the transfer function is computed for display, it will be reference to this text1 tag. So that we can see in this code. So here first the system, I mean the transfer function is calculated with the TF function. So handles.num comma handles.den. Okay, so your transfer function is computed, and then this is evaluated in strings, I mean in form of the characters, and then see this set. Set means display this computed transfer function to the text area. So you can see that text1. So that is the tag name of that text area on which this has to be displayed in form of the string, right? So when you compute this, your computed transfer function will be displayed. So you have to insert only these 3 lines. And now this is the callback for a UI button group selection change function. So here you can see that all 8 radio buttons in this panel, I mean radio button group. So here these lines are written by the MATLAB automatically, and this is my code which you have to insert. So here I am using the switch case control statements. So switch get the event data dot new value tag. I mean whenever you select any radio button, the corresponding value you will achieve. So if you select the first one whose tag is actually the radio button 1, if you select this first one, then the output will be the radio button 1 string, and if you select the second one, the output will be the radio button 2 string. So here you can see that case radio button 1. So if you select first one from this get, you will get this string radio button 1. If you select second, you will get this string radio button 2. So depending on the selection, I am just taking one variable and setting the corresponding value. So this is my variable response, and I am making handles of it so that I can use this across the callbacks. So I am simply assigning the values. So if I select the impulse response, the variable value is 1. If I select the step response, the second radio button, then the value of this variable is 2, like that. Simply I am assigning the 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then ending the switch, and then updating the GUI data. So this is simple one. You have to insert these lines in the UI button group selection change function. And now let's see the final one, and that is the compute button. So that is the push button callback, push button 2, whose tag name is push button 2. So these are automatically generated lines, and from here you can insert this code. So case 1. Case 1 means somebody has selected the first radio button. And what is the first radio button? That is the impulse response. Impulse response. So with these lines, I am computing the impulse response of that transfer function. Okay. So with the MATLAB inbuilt function impulse, I am computing the impulse response, and other lines are just for display purpose, making that plot better. And in the case 2, first CLA actually the clearing the axis, so it can be used to plot a new curve whenever you select a new radio button. And then with help of the step function, I am plotting the step response. And then case 3 means where I am selecting the ramp response. So for this type of input, you will get some ramp response. Okay, so ramp response is actually MATLAB has no inbuilt command for the ramp response. So with help of the step response, I am finding the ramp response. How it is possible? For example, let's say my function is s plus 25 upon s square 2s plus 25. and I want to find the ramp response. So the output upon input CS upon RS is this. So output CS equal to this transfer function and RS, right? So CS equal to this transfer function, and RS is a ramp input. So RT is your input, and Laplace transform is 1 upon S square for the ramp input. So I will write 1 upon S square. Okay, if I take 1s inside to the transfer function, okay, I just take 1s inside, 1 upon s, and the remaining one will be 1 upon s. So when I insert 1s, that means I am multiplying the denominator with the 1s. So my denominator will be simply s cube plus 2s square plus 25s. Okay, so this is my new transfer function, so that you can insert here just by multiplying s in the denominator. So whatever the modified transfer function you have, if you see the carefully, this is 1 upon s outside. So 1 upon s outside means you are finding the step response of this modified transfer function. So you have to multiply by s in the denominator and taking step response of that modified transfer function, you will get the ramp response. Okay, so that I am doing the same here. And case 4, where I am finding the frequency response with help of the Bode. So MATLAB has the inbuilt function Bode, where you have to pass the numerator and denominator. And in case 5, I am plotting the root locus. So MATLAB has an inbuilt function R locus, again passing numerator and denominator values. And in case 6, I am plotting the Nyquist. Again, I am utilizing the inbuilt function Nyquist. And in case 7, Nyquist, that is used for plotting the log magnitude versus phase plot. So again, it MATLAB's inbuilt function. And for pole 0, I am again using the MATLAB inbuilt function, that is PZ map. Okay, I am doing some modification in the plot to make it better, okay, for better visualizations. Actually, MATLAB default PZ map creates a very dull looking plot where very small size or small markers are there, which are hardly which are difficult to see or visualize. So here I am just modifying the plot with the different colors and different marker size, so making the bigger poles and zeros in the plot, and then updating the GUI data. So this program is complete. You have to insert all these callback codes to their corresponding location. Once this is done, now your program is ready to run the simulation. So let me jump to the MATLAB and let me show you that this program is already written. So let me show you the edit one. So this is the edit one callback, and here you can see that I have inserted these 3 lines of code, and in edit 2 callback I have inserted these 3 lines of code, and in push button 1 I have inserted this, and in push button 2 I have inserted the switch case statement, all these commands which I have already shown you in the slides. And in this UI button group 1 selection change function, I have inserted this switch case commands which I have already shown you. So this my program is ready, and now I am running this program, and let me show you what output I will achieve. So this is my GUI, and here you can see that you can enter the numerator. So let me enter the same transfer function, that is s plus 25. So 1 25, and numerator and denominator is s square 2s plus 25, and just pressing this find TF, you will see that your transfer function is displayed here in that text field, text 1 tag. So s plus 25, s square plus 2s plus 25. Okay, now from here you can select any of the analysis. So I am selecting the impulse response first, and then pressing this compute button. Okay, so when you press it, you will get the corresponding impulse response, you can see. And when you select the step response and just press compute, you will get the corresponding step response. You can see that we are getting a line on a red line on the 1. That means that was the input step, and this is blue one is the corresponding response. Then selecting the ramp response, compute, and this is the ramp response. The red one is your input straight line, and these this blue one with the oscillations is your ramp in response. And here you can see that there is some steady state error because your output is lagging the input by some constant after some time. And then frequency response, select this, compute, and yes, you can see the Bode diagram here. So here the magnitude and the phase both you can see, and then root locus. So this is the root locus. It has this function has the 2 roots and 1 0. Okay, so one pole ends its journey at the 0, and other pole goes to the infinity in search of 0. And the Nyquist, this is the Nyquist, the Nichols, there is a log magnitude curve, and then pole 0 plot. So here you can see that this is the 1 0, which is lying at this real axis at minus 25, and 2 poles, complex poles. Okay, so this GUI has actually the capability to show you the more details. So if you take your cursor on the 0, you will see the corresponding information. So for example, you can see that your 0 is at minus 25, damping is 1, it is providing 0% overshoot, and frequency is 25 radian per second. And when you go to the poles, you can see that its value is minus 1 plus minus 4.9 I or J, and it is providing damping of 0.2, and it is providing overshoot of 52.7% at frequency 5 radian per second. Similarly, if you click this, you will get the corresponding detail. The same detail you can find in the step response also. So when you press step response, just right click here and you will see the characteristics. So in characteristic, if you click this peak response, you will get the corresponding peak response. So just click it, you will get the peak amplitude is 1.54 corresponding to the 53.8% maximum overshoot at the time 0.599 seconds. Similarly, just press it again and you can find the settling time. So settling time is 3.89 seconds, and then rise time, the rise time is 0.235 seconds, and then steady state. So steady state is 1. So that means steady state error is 0 in this case for the step response. Okay, similarly in the frequency response, when you go to this Bode diagram, you just right click in the characteristics, just simply press this all stability margins. So when you press this all stability margins, you will see this dot. So just click it, you will see that corresponding phase margin is 47.3 degree, delay margin is 0.12, at the frequency 6.86. The closed loop system is stable, yes. So the closed loop system is stable. So all corresponding stability details you can find from here, and in the root locus you can also have the corresponding details. So when you press on the pole, okay, again you will get the same detail, like the gain is 0. In the root locus we know that the poles are starting points, so where gain is 0, and the pole location is minus 1 plus minus 4.9 I. Okay, when you press the 0, you will see that gain is infinity, INF, and we know that in root locus zeros are the end points, so obviously the gain is infinity here, and you can find that damping is 1 and the frequency here is 25 radian per second, like that. So all corresponding details you can find from these plots. Similarly, in the Nyquist plot you can find the stability. You just right click in the characteristics, all stability margins. So the unit circle is plotted. So you can see the unit circle, and on this plot when you click it on this point, you will see that the corresponding phase margin is 47.3. It is same which you achieved in this Bode plot at the frequency 6.86 radian per second. And the closed loops stable, yes, it is closed loop stable. So from this Nyquist you can find the corresponding stability. Similarly, from the Nichols plot you can find the stability. Just right click, characteristic, and the all stability margins. So you will get this dot and the stability margin. So when you click it, you will see the same information again. The phase margin is 47.3 at the frequency 6.866 radian per second. Closed loop stable, yes, it is closed loop stable. So this is really a very nice GUI. With help of it, you can analyze any LTI system. You just give the numerator and the denominator coefficients. You can analyze any LTI system here. You can see their corresponding curves. And also, if you are doing some numericals related to that LTI system, you can verify your answers also. Suppose you are finding some peak response or settling time, rise time, etc., or you are plotting the Bode plots and you want to find the phase margin, etc. You can verify your results in control system theory, right? So I hope you have enjoyed this video tutorial. So thank you very much for giving your time and watching this video, and stay tuned with me for more such interesting videos to come. Have a nice day.